Calibration, this new Google quantum computer, but the amount of power in computing is incomprehensible. But the idea is that they're pulling answers from different universes.
Imagine a hidden design coming from the heart of one of the fastest computers on Earth. Beneath the circuits and the qubits, researchers found a shape that should vanish but does not. It appears again and again like a pattern from another realm. It defies expectations and creates a lot of questions about every bit of computation. Something known as the Omega pattern has shown up in Google's quantum machine. What is it? Why does it persist? To trace the Omega, you have to understand the machine that made it. And Sycamore is no ordinary computer. Prepare to dive into the unseen code. When bits become qubits, meet Sycamore. Google's Sycamore quantum computer uses a grid of tiny circuits called superconducting qubits. Each qubit is a loop of aluminium metal cooled to about 10 millikelvins inside a dilution refrigerator that stands as tall as an adult and chills the chip near absolute zero. At that temperature, electrical resistance vanishes, and qubits can hold their quantum states long enough to run complex experiments. Each qubit sits on a flat, square grid and links with up to 4 neighbors through microwave buses that let them share information in a fraction of a microsecond. When the team at Google's Quantum Artificial Intelligence Lab first lit up Sycamore in 2019, they calibrated 53 qubits and ran a random circuit sampling task. That meant applying sequences of quantum gate operations to shuffle qubit states in a controlled pattern. Each gate is a carefully timed microwave pulse lasting just tens of nanoseconds. A single pulse can flip a qubit between its 0 and 1 states. Some pulses entangle pairs of qubits so that measuring one gives information about the other. Timing and power must be precise because tiny errors can collapse the superposition. By running 1 million samples of a random circuit with about 20 qubits and 30 layers of gates, Sycamore generated a final distribution of outcomes in roughly 200 seconds. A classical supercomputer, even one as powerful as Summit at Oak Ridge National Laboratory, would have needed about 10,000 years for the same task, according to Google's estimate published in the journal Nature. That benchmark became known as quantum supremacy, marking the first clear moment when a quantum device outpaced all known classical machines. Building and controlling that chip required solving problems at multiple levels. At the hardware level, engineers crafted each qubit as a transmon device, a pair of superconducting islands separated by a thin insulating barrier called a Josephson junction. That junction provides a nonlinear inductance that holds 2 energy levels for the qubit. Qubits share coplanar waveguide resonators that read out their state. After each gate operation, the team sends a measurement pulse into the resonator. The resonator's response shifts slightly, depending on the qubit's state. Low-noise amplifiers then boost that signal so it can be recorded without destroying the qubit's superposition prematurely. To shield the chip from stray magnetic fields, researchers encased it in a layer of magnetic metal and added infrared filters that block high-energy photons. Control electronics sit outside the cryostat and connect through filtered coaxial cables. Those cables scrub noise so only clean signals reach the qubits. After each experiment, reset pulses clear any leftover excitations by dumping energy into special resonators that act like drains for qubit excitations. A proper reset is vital because any residual energy can distort the next run. Software ties all these parts together. A scheduler coordinates gates to avoid crosstalk when 2 pulses overlap. Before each run, calibration routines measure qubit frequencies, coherence times, and gate errors. Qubit coherence indicates how long a superposition lasts before noise collapses it. On Sycamore, typical coherence times lie between 50 and 100 microseconds. That window is long compared to gate times, but still requires swift execution of deep circuits. Sycamore's achievement in 2019 was built on past work at IBM and Yale labs that demonstrated 2-qubit entanglement and small-scale algorithms. Scaling from 2 qubits to 50 required new chip designs and tighter integration among fabrication, cryogenics, and control software. After the first milestone, Google added more qubits and refined hardware. Later versions of Sycamore expanded the grid to 70 qubits. They also improved gate fidelity. Error rates for 2-qubit gates fell to well below 1% in key tests, and single-qubit gates reached error rates under 0.1%. Teams around the world use Sycamore to explore real applications. Computational chemists simulate small molecules to predict energy levels and reaction paths for new catalysts. Optimization specialists map puzzle-like problems onto quantum circuits to test options for vaccine design or traffic flow. Error correction researchers build logical qubits from multiple physical qubits. By encoding a single logical bit across several qubits, they aim to detect and correct errors on the fly, a crucial step toward fault-tolerant machines. After the milestone run, IBM researchers argued that Summit might solve the same circuits in just days instead of 10,000 years, which led to more precise benchmarking and new classical simulation methods. That discussion drove work on error correction codes, including small surface code tests that group qubits in arrays to detect and fix errors. Google's lab in Santa Barbara brings together over 70 experts who use clean rooms and advanced deposition tools to build each superconducting circuit and test it under various conditions. Google envisions linking Sycamore modules via microwave couplers to scale networks beyond 100 qubits. Sycamore sits at the forefront of quantum hardware design and integration. Its design forms a template for future devices both at Google and in research labs around the world. Understanding how Sycamore works, its transmon qubit design, accurate microwave control, and intense calibration provides the foundation for making sense of any unusual behavior that appears in advanced simulations. It was against this backdrop that researchers preparing for dark energy analog experiments first noticed the Omega pattern. But just as they were pushing the boundaries of dark energy simulations, something unexpected slipped through the data. A pattern no one could quite explain, and it didn't look random. It looked deliberate. That strange Omega knot, a researcher named Daniel Ferreira, working with a small team at Google's Quantum AI lab, published a technical report describing a strange shape that appeared in the data from Google's Sycamore quantum processor. The team had been conducting simulations that tried to recreate the behavior of dark energy, a mysterious force that seems to push the universe apart and make it expand faster over time. To do this, they created a model Hamiltonian that mimicked a scalar field with repulsive interactions. They then used Trotter decomposition, a standard technique in quantum simulation, to break the Hamiltonian into time steps. Each of these steps was mapped onto a series of quantum gates acting across the Sycamore chip's 53 qubits. After each run of the circuit, the control system reset all the qubits to their lowest energy state, called the ground state. This reset was done using microwave pulses that passed through special resonators. These resonators drained out any remaining energy from the qubits, effectively giving the machine a clean slate before the next run. This was important because quantum experiments are very sensitive to leftover information from previous operations. But even with perfect resets, the team started noticing something strange in the data. During the dark energy simulations, when they analyzed the entanglement structure between qubits, a peculiar shape appeared. It looked like a loop connecting several qubits. When mapped onto the grid of the qubit layout, the loop formed a closed ring that closely resembled the Greek letter omega. The pattern kept showing up again and again in the same region of the chip. Because of its distinctive shape, the researchers started referring to it as the omega pattern. At first, the team assumed this was just a hardware or measurement error. quantum measurements depend on delicate amplifiers that detect tiny signals coming from the qubits. If an amplifier glitches or introduces noise, it could create false correlations between the qubits. To rule this out, they replaced the amplifiers, used different cables, and even moved the whole experiment into a different cryogenic system. However, every time they ran the dark energy simulation again, the omega loop came back. This strongly suggested that the effect was not due to faulty components, but rather something happening within the computation itself. To further isolate the cause, the team ran control experiments, using circuits that were completely random but matched the same number of gates and layers. These random circuits showed no sign of the loop. They also tested other known quantum models, such as molecular simulations and spin chains, which also failed to produce the omega pattern. The loop only appeared during the dark energy simulations, suggesting that it had something to do with the logic and structure of that particular model. To visualize the pattern, Ferreira's team created a heat map. This map plots the joint probabilities of measuring pairs of qubits both in the one state. On this map, each square represented a pair of qubits, and brighter colors indicated stronger joint activity. When overlaid onto the physical layout of the Sycamore chip, the bright spots connected in a loop across 8 specific qubits. No matter how they adjusted the color scale or filtering thresholds, the loop remained visible. They then changed the time steps in the simulation. Some runs used shorter steps and more gate layers, while others used fewer steps but longer durations. Still, the omega loop appeared in the results. They also shifted the starting point of the simulation, meaning they began with a different group of qubits, but the loop still formed and moved accordingly. This confirmed that the loop was not tied to fixed hardware quirks, but to the logical sequence of operations within the circuit. To dig deeper, the team performed a partial tomographic scan. This means they measured 2 qubit expectation values across a small section of the chip, looking for signs of stray activity, crosstalk, or uncontrolled excitations. The results showed no unusual behavior, only minor offsets consistent with thermal noise and calibration limits. Nothing in the scan could explain why 8 specific qubits would form a ring. In total, each dark energy run included over 1,000 quantum gates, pushing the circuit depth to a high level. The team repeated the experiment 500 times, collecting statistics. The qubit pairs forming the omega loop showed correlation levels nearly twice the usual noise threshold, with a statistical significance greater than 3 sigma. This means the pattern was unlikely to be a random fluctuation. To confirm their findings, Ferreira's group built a software model that simulated the same circuit using detailed noise profiles from the actual hardware. This included known sources of error like gate infidelity, readout errors, and thermal drift. Interestingly, the software model did not produce the omega loop. This pointed to the conclusion that the loop was not caused by any known error mechanism that current models could simulate. Finally, they tested whether the physical layout of the chip mattered. Google has built several variants of the Sycamore grid with different qubit connectivities. When the same dark energy circuit was run on a chip with a different layout, the loop disappeared. This finding emphasized that the omega pattern depended on both the simulation logic and the specific hardware structure used in the original experiments. The discovery raised serious questions across the quantum community. One key principle in quantum computing is the blank slate assumption that a qubit, once reset, has no memory of past operations. If patterns like the omega loop suggest hidden memory or residual entanglement between runs, this could challenge current approaches to quantum error correction and device calibration. Ferreira's group stayed cautious. They made it clear that the omega pattern was a lab observation, not a claim of new physics. Until other labs reproduced the effect using different machines and methods, it remains a mysterious phenomenon. However, the loop may hold secrets that could lead to a better understanding of qubit dynamics, or even open the door to new tools for stabilizing quantum information. Pressing reset, and it came back. In quantum computing, each experiment begins with a clean slate. That is essential because leftover energy or signals can interfere with new data. Google's Sycamore chip uses a reset sequence after every test to ensure all qubits return to their ground state. The reset starts with microwave pulses sent through resonators connected to each qubit. These resonators act like drains, removing any leftover excitations from the system. After that, the chip sits idle for a short period. This pause allows any residual energy to naturally relax before the next computation begins. Resetting depends on two main properties of qubits. The first is T1 time, which measures how long a qubit remains excited before it naturally returns to its ground state. On the Sycamore chip, T1 typically ranges from 20 to 50 microseconds. The second is T2 time, which measures how long a qubit maintains its phase information in a superposition before that coherence is lost due to noise. T2 values are usually between 10 and 30 microseconds. An effective reset must be completed faster than these times to prevent interference from lingering signals. Google's researchers used a standard reset for their dark energy simulations. A few microseconds of active reset pulses, followed by a 10 microsecond idle. They verified the qubits were cleared by measuring them, and all reported zeros. Then they ran the simulation. Surprisingly, the same omega loop pattern appeared in the data again. This result suggested something within the chip retained information across resets. That was not supposed to happen. In theory, each run should be isolated. If the reset worked correctly, no feature from a previous simulation should reappear. Yet the omega loop persisted. To investigate, they began varying the reset procedure. They shortened the idle time to just a few microseconds. Then they tried extending it to several milliseconds. They added dummy gate cycles, useless operations meant to scramble any leftover quantum state. They even repeated the reset sequence twice. Still, the omega pattern came back. The changes had no noticeable effect. This pointed to something deeper. Whatever was causing the loop was not removed by standard clearing methods. It seemed embedded in the system, not just residual energy or noise. It hinted at a long-lived memory effect inside the quantum hardware. They performed scans of T1 and T2 before and after each simulation. If any qubit was behaving abnormally, holding energy too long, or losing phase too quickly, it should have shown up. However, the results showed stable expected values. There were no outliers. Coherence times and error rates stayed within the usual margins. Nothing suggested that a specific qubit was faulty. Next, they turned to quantum process tomography. This method tests how sets of qubits behave under known inputs. It reconstructs how quantum gates affect qubit states, detecting any hidden crosstalk or unintended couplings. They applied this analysis to the qubit group where the omega loop had formed. The tomography results revealed only expected minor calibration issues, nothing that could account for the repeated loop structure. They then ruled out software. The team built a full simulation of the dark energy sequence using classical computers. This included every measured hardware imperfection, decoherence, gate error, and noise model. The simulation mirrored real device behavior as closely as possible. Hundreds of runs showed no sign of an omega loop. If software or simulation logic had been the problem, the loop should have emerged here too, but it did not. To eliminate hardware-specific quirks, they ran the same experiment on a second Sycamore chip in the same lab. This chip shared the same architecture and performance, but had different physical hardware. Once again, the omega loop emerged. That suggested the effect was not tied to a single chip defect. It could be something deeper in Sycamore's design. Looking for more clues, the team tested the same simulation on a different chip layout, one with a non-grid structure. In this alternative configuration, each qubit had fewer neighbors and a different connectivity pattern. When they ran the experiment on this chip, the omega pattern vanished. No loops appeared in the entanglement data. This was a major clue. The grid layout of Sycamore, with its structured qubit connectivity, seemed to play a key role in the pattern's emergence. Something about how qubits were physically linked and how timing interacted with that structure appeared crucial. The loop may have been a product of deep interactions between simulation logic and the geometry of the chip. Google's team is now experimenting with variations in hardware layouts, gate timing sequences, and advanced reset mechanisms. They are also looking at error correction strategies that might reveal or suppress these long-lived correlations. It remains unclear if the omega loop represents a flaw, a feature, or something entirely new. The appearance of a stable, repeating pattern across multiple resets, chips, and configurations has raised questions. Are current reset protocols truly effective? Or is there an unknown depth to quantum hardware behavior that standard models miss? Could this be a trace of some hidden quantum phase or a side effect of entanglement propagation through the chip's structure? For now, the team admits the loop resists all known explanations. It defies expectations in a machine that is supposed to forget everything. The omega loop may be pointing at something we do not yet understand, something subtle that lives between coherence and noise, between logic gates and hardware wiring. As researchers dig deeper, they hope to learn whether this recurring shape is just a ghost in the machine or a new pattern waiting to be decoded. Is reality playing tricks on us? The omega pattern led to a range of ideas. One suggestion centered on hidden error correction routines built into Google's control software. In theory, when certain error rates or noise thresholds are triggered, the system could apply correction pulses to protect qubit states. People wondered if those correction pulses, interacting with the timing of the dark energy simulation gates, might weave the omega loop as an unintended side effect. That theory raises questions about how much of Sycamore's behavior is driven by real qubit physics and how much by background software safeguards. Another idea drew on the old simulation hypothesis. If our universe runs on an underlying quantum computer, glitchy patterns might surface under the right experiments. In this view, the omega loop could be a debug marker or memory artifact left by the simulator. While this notion remains pure speculation, it gained traction among hobbyist physicists who delight in pondering whether a cosmic coder tested the pattern before erasing it. Classical effects also made the rounds as explanations. Dark energy simulations require rapid, high-frequency microwave pulses to mimic a repulsive force. Some pointed out that those pulses could excite standing wave currents in the metal layers beneath the qubit grid. Those currents can form loops of higher intensity in predictable shapes. If those classical loops overlay the qubit positions, the measured entanglement hotspots would trace the same ring. In that case, the omega pattern would be a classical imprint, not a quantum memory. The loops were even compared to magnetic domain walls in certain alloys. When you apply and then remove a magnetic field, the boundaries between domains can snap into loop shapes and then reform on each cycle. Could stressed superconducting films under pulsed drives act similarly? It is an intriguing parallel that suggests studying the chip's material properties more closely might reveal hidden effects. On the flip side, some theorists warned that human pattern seeking can be misleading. In complex datasets, random clusters can look like meaningful shapes if you only focus on the most vivid examples. Changing color scales, or how you threshold the data, can produce different rings, triangles, or other forms. A handful of quantum architects speculated that the omega pattern might hint at a new phase of entangled matter. In condensed matter physics, Certain systems form topological phases with protected edge states that resist local perturbations. If Sycamore's qubits under those dark energy gates entered a similar phase, they could spontaneously form a looped correlation that resets stubbornly. That idea would open doors to novel error-resistant designs, but it stands on the faintest of evidence. Within Google's lab, engineers treat the Omega pattern as a curious puzzle. They keep their test results under wraps while they run more experiments. A few slides were labeled Omega Oddity across internal presentations. That silence only fuels more rumors outside the lab. Despite the swirl of conjecture, everyone agrees on one point: more data is needed. Teams plan to test other simulation targets, such as analogues of weak and strong nuclear forces, to see if similar loops appear. They will also vary pulse shapes, gate orders, and cooling cycles to pinpoint the exact cause. Independent labs in Europe and Asia have signaled interest in replicating the experiments on their own superconducting and ion trap platforms. The Omega pattern debate highlights the fine line between error and discovery in quantum hardware. When every run resets to 0, any repeatable pattern challenges our ideas about qubit memory, noise models, and control software. Whether the Omega loop proves to be a clever signal from deeper physics or just an artifact of control pulses, it has already made one thing clear: our understanding of complex quantum machines is still incomplete. As the community chases answers, the story of the Omega pattern becomes a live case study in keeping an open mind. In a field where every anomaly could signal the next big advance, or simply a misunderstood glitch, patience and careful testing remain the surest path forward. And just when you think you've spotted something revolutionary, boom, the skeptics come knocking. Because in quantum science, every breakthrough starts out looking a lot like a blunder. Do not call it a breakthrough yet. Long before the Omega pattern arrived, researchers treated strange data with caution. In 2022, a team said they saw a wormhole in Google's Sycamore chip. They ran a cloud of interacting qubits described by the Sachdev-Yekitaev model. They observed information sent into one group of qubits reappearing in another group as if it passed through a tunnel. The claim made headlines until other experts said the effect could come from random fluctuations in small samples. At the same time, a team led by Pan Zhang in China used more than 500 graphics cards to copy Sycamore's famous 2019 task on classical hardware. They found that classical machines could sample the same circuits in just days instead of 10,000 years. That work showed that classical and quantum methods push each other forward. It also made it clear that any new claim about quantum advantage or odd patterns needs careful proof. Errors remain the biggest challenge in quantum work. A single gate can err at 1 part in 100. In a circuit with 1,000 gates, most runs see many errors. Readouts can also misreport the final state of each qubit. When data has many such errors, it can look like real effects. Labs measure error rates before each run. They adjust pulses and rerun calibration routines to keep errors low. Yet, small drifts over time can still cause false patterns. Another enemy is crosstalk between control lines. Microwave pulses travel along metal traces under the chip. Those traces can vibrate like strings on a guitar and leak signals into nearby lines. Even with filters, some energy can jump from one qubit to another. In a long simulation, crosstalk can create loops of bias that map onto qubit pairs. Any new loop must clear thorough crosstalk tests before it can be called evidence of new physics. Calibration drift also hides in plain sight. Shields of metal around the chip can gain or lose tiny magnetic particles. Those particles shift qubit frequencies by a few megahertz each day. Control electronics heat up and change their timing. To fight that, labs run calibration scans before and after each experiment. They check T1 and T2 times, gate fidelities, and readout errors. Even so, hidden drift can slip through and show up as strange rings in correlation maps. Surface code tests add another layer of security. In those tests, several physical qubits form a logical qubit that can correct single-bit or phase flips. If errors are uncorrelated, the code catches them, but if errors link qubits across the grid, the code can fail silently. The Omega pattern might come from such linked errors. Some labs have already begun running small surface code blocks under dark energy sequences to see if loops appear in logical data. Efforts to reproduce the Omega shape on other platforms are underway. At ETH Zurich, a group ran the same dark energy circuits on a 60-qubit superconducting simulator. They found no clear loop at their current circuit depth. In Tokyo, a team used an ion trap with 20 qubits. They saw hints of a ring in 2 out of 10 runs, but the result was weak. Photonic and neutral atom platforms have not reported any similar pattern yet. History has warned us before. In 2011, the Opera experiment said neutrinos moved faster than light, only to find a loose cable at work. In 2014, cold fusion burst into view until flaws in cell design came to light. In 2015, early signals of gravitational waves from the Big Bang turned out to be dust in our galaxy. Each time, initial excitement gave way to more tests and improved methods. Quantum computing must follow that same clear path before calling any pattern a real discovery. To steer clear of wishful thinking, labs plan blind tests next. In those tests, dark energy runs will mix with random sequences that the data team will not know. Only after analysis will they learn which runs were which. If the Omega loop appears only in the dark energy ones, confidence will rise. If it shows up in random runs, the case for a real effect will weaken. Theorists also offer ideas for new physics. One idea borrows from many-body physics and suggests that certain gate patterns can create a metastable loop of entanglement that outlives resets. Another idea looks at quantum scars, where the system revisits certain states over time. Those scars can form ring-like shapes in state space. However, these ideas need strong evidence from multiple platforms before they move from theory to fact. Error mitigation methods like randomized compiling aim to distinguish real effects from errors. Randomized compiling mixes random gate sequences to average out coherent errors. In zero-noise extrapolation, the same circuit runs at higher noise levels to extrapolate back to the ideal case. Researchers will test if the Omega loops remain after applying them. Teams in North America have started using those methods on dark energy circuits. They plan to test other quantum routines, such as chemistry models and benchmarking tests, to see if the loop is unique. No matter how it ends, the Omega pattern drives home how little we know about complex quantum machines. It shows that even with careful resets, hidden effects can arise. It reminds us that proof demands repeated tests and cross-checks across platforms. Until labs agree, the Omega loop remains a puzzle, not proof of new physics or hidden memory. Researchers will keep testing, refining, and sharing results. And when the mystery finally resolves, we will have learned more about the promise and the limits of quantum computing. What will tomorrow's tests reveal about the Omega pattern? Will it vanish before our eyes, or open a new chapter in quantum science? Keep your eyes on our channel for the next deep dive. If you enjoyed this mystery tour through the quantum core, please like, comment, and subscribe. We will discover more of tech's best-kept secrets together.